last video, we talked about the different spheres and how they relate to climate change. Now we're going to talk about the natural causes of climate change. The climate changes. This is known to happen. It's a normal, natural part of the Earth system, and it's been studied for as long as there's been science. So let's just talk about them. One of the ones that gets a lot of attention is the solar energy change, especially because we just hit the peak of our solar cycle a year and a half ago. Solar energy does change over time. It is not consistent. The sun goes through cycles of approximately 11 years where it gives off more energy. You probably heard, when was Coriata Senior? 2 years ago, about the solar storms that were happening. The Aurora Borealis was visible down here. This last image in the top picture right here, you can kind of see a solar storm. So that is a natural factor that could possibly change over time. One of the problems with it in terms of climate change, though, is solar energy alone. It changes by 0.1%. So let me show you. This is a graph of the solar. It's really called luminosity. And if you look at the scale here, we're dealing with watts per meter squared. That deals with energy entering the atmosphere, and how much. And if you notice the scale for the graph, it goes from 1365 as the high point to 1360. So keep that in mind when we're talking about the 0.1%. It changes very, very little. So we can't really blame the current climate shift on changes in solar energy. One thing that we absolutely know causes changes in the climate is Milankovitch cycles. I cannot overemphasize how important these next few slides will be. Milankovitch, so important. Oh, I'm jumping around. There are three parts of the Milankovitch cycle, so there will be 3 slides. The first part has to do with eccentricity. Hold on one sec. I wanted the video to play again. Eccentricity is due to the gravity from other planets, particularly Venus. Venus is kind of close to us and has a similar size. And basically what it does, and this is grossly exaggerated in this little GIF, is that it changes the path of the Earth's orbit around the sun a little bit. So it goes from being elliptical to like more elliptical. And what this means is that sometimes the Earth is closer to the sun on its path than it was in years before. And these cycles happen between around 9,500 years. But there are super cycles at the 125 to 400K 400,000 years. So this is one of the big causes of natural climate change, is eccentricity of the orbit. Also, there's obliquity. Obliquity in some books is called axial tilt. They're the same thing. This is actually due to the declination of the moon, which, as you remember, hopefully it was only 2 chapters ago, is the moon is not rotating directly over the equator. So sometimes it's like the barycenter moves along the surface of the Earth, and as you know, the Earth is not a perfect sphere, it's a spheroid. So that change in the barycenter, the center of mass of the system, actually causes the Earth's tilt to change. It's like 11 degrees. This shows like 45 in this diagram. Again, gross exaggeration. And these changes happen on the 41,000-ish year cycle. So that's obliquity. You can also, and hopefully you remember, that the tilt of the Earth controls how hot the summers are and whatnot. So as this tilts towards the sun, the ice shields would be getting more light and thus would potentially melt more. So that's how obliquity can cause changes to climate. This one, I hate both of these pictures, but together they're not too bad. It's a shame this one just stopped spinning. It's precession. Precession, is always likened to spinning a top. Precession takes into account the sun and the moon acting differently on the surface of the Earth, and they cause the Earth to begin to wobble. So like if you spin a top and you let it spin, sometimes it's fine, and then sometimes it wobbles while it's still spinning. That happens to the Earth as well. And that happens at about every 26,000-ish years, give or take a little bit. These 3 things together lead to those Milankovitch cycles. So Milankovitch is not the guy who discovered this. He's just the guy who put it all together. And so we have precession at the top, then obliquity. And where these line up, if you notice, this kind of peaks here, and this peaks here, and this peaks here, and we would get a glacial minima. Places where they're really low, like here and here and here, we get a glacial maxima. A glacial maxima, by the way, is an ice age. Glacial minima is a warming period. I guess those are words I should have underlined. So the Milankovitch cycle is definitely something I'm going to be asking you. Oh, by the way, this thing about solar forcing, don't worry about it. I'm not going to ask you about it. But these three, you got to know. And the Milankovitch cycles are fairly awesome in terms of their ability to predict past climate. We like them very much. They are one of the better climate predictors of all time, 99 some odd percent. But there are a couple issues that they're still working to resolve in its ongoing research right now. One of the issues is that the effect exceeds cause. And what this means is that even if you take into account, add all of these things together, that precession brings us closer to the sun. Obliquity tilts us more to the sun, and the wobble tilts the whole Earth closer to the sun. That would make the planet warmer, and we would enter a period of, minimal glaciation. Even when you add them together, we actually get an exponentially larger effect. This is true in both the hot and the cold stages. So the effect exceeds cause. So there are clearly other things, and this is where the solar forcing comes in, and a million other little tiny things that add up when these happen to create glaciation or no glaciation, as the case may be. One of the classic examples is marine isotopes. Marine isotopes, especially boron-13, is used to tell temperature, ocean temperature. And what's interesting is for at least the last 5 glacial periods, the marine isotopes were showing changes in temperature 10,000 years before the Milankovitch cycles actually shifted. So that's kind of fascinating in terms of climate science and what it all means. Volcanism is another natural cause of climate change, though we need to be careful. Not all volcanism causes climate change. Volcanoes emit this amount, this 0.1 to 0.3 gigatons of carbon dioxide a year. And this is a lot. It's actually one of the largest natural sources of CO2 in the atmosphere. But it's quite a bit smaller than what humans do, orders of magnitude smaller. And this amount is more stable, so it's taken up more easily by systems. In fact, some organisms count on it. This CO2 is actually initially offset by a cooling period, usually a 1 to 2 year cooling period for any major eruption due to the pyroclastic ash making it to the upper levels of the troposphere, where that dust increases the troposphere's albedo for a while. So that white ash reflects more light, and we have less absorption. So it actually has a cooling effect. You can see that with Mount Pinatubo, that there was quite a bit of cooling for the next 2 years after it. In order to have a real climate change, you would need a mega eruption. These are periods of very large eruptions, and even then you'll just have minor climate events, such as the Little Ice Age. They tend to be more localized in areas with more land, like Europe. So like impact events, you can absolutely have volcanic winter, just like you could have an impact winter, God forbid, nuclear winter. But it's rare, and we would know if there was that much volcanism going on right now, and there's just not. Plate tectonics has been known to have massive effects on climate, especially in the past. This is a picture of Pangea, which you probably heard about in middle school. Almost all of the continents as we knew them were one big landmass. This meant there was one global ocean, and that ocean encompassed the Arctic and the Antarctic were basically connected in one ocean. The thermohaline circulation was very, very different then. And because there was less landmass, because there was less coastline and whatnot, it changed the amount of albedo and absorption. And if you notice, all of the land here tends to be centered around the equator. We actually have only a moderate amount of land, like 50-50 land water at the equator. That has an influence on heat absorption, how much is absorbed by water, how much is absorbed by land. So plate tectonics could absolutely change climate. It has. We know for a fact that Antarctica was not where it was. Now that it's there, it acts as a little reflecting mirror, and not that little at that, it's the largest continent. A reflecting mirror down there, reflecting a large amount of light. And it didn't do that historically. It was actually covered by forests at one point. So yes, climate change is due to plate tectonics is very, very possible. Unfortunately, it's also very, very slow and would be really obvious because we'd be moving around. So it's not likely that the current climate change is related to plate tectonics. I mentioned them already a little bit. There was the last ice ages, was the Pleistocene ice age. As a species, we survived that. We actually, Homo sapiens sort of evolved during the Pleistocene ice age. Glaciers only came down to like Wisconsin and kind of went across to Long Island then. And we actually are not sure what caused the Pleistocene to begin or end. That's something that's hotly researched right now. It was definitely linked to Milankovitch, but not enough. It was actually one of the longer ice ages. The Little Ice Age you've probably heard of. It was a period of cooling that actually was three small periods of cooling in the 1600s, 1700s, and even the 1800s. And this was actually, the Little Ice Age was actually probably closely related to volcanism, and then to a lesser degree by ocean currents. The medieval warming period after so there was the Pleistocene, and then there was a geological time later, there was a medieval warming period. And those last Canadian glaciers that had been retreating for quite some time had an ice dam, which sort of blocked them. And that ice dam let go. It finally melted. And thousands and thousands of cubic kilometers of fresh water flooded into the North Atlantic. This was very cold and it was very fresh. Because it was very, very cold because it was functionally ice water, it had a huge impact on North Atlantic circulation. And there's evidence to suggest, based on the lack of oxygen at the bottom of the ocean during this time period, that it shut down thermohaline circulation. And as you know, the Gulf Stream warms Europe. So it and definitely had part of the Little Ice Age was due to that. And we're going to talk about the IPCC and human-caused climate change next video.